So, on to our second query. What is this course all about?
This is the universal symbol for a database, a cylinder or a stack of cylinders like this. And that's not a coincidence. A database system icon looks very much like the platters on a traditional magnetic disk drive. So the picture on the right is a fairly modern disk drive, and you can see that it has three platters, each of which is a disk or a cylinder, and they're stacked up to make something that really looks like a cylinder. And if you go back in time, this is the first disk drive, the IBM Model 350 RAMAC, which stored 5 megabytes and weighed 1 ton. Okay, 1956, pretty impressive. Looks very much like our icon for a database. An interesting quote from that time, going back in database history, an IBM senior manager, F.J. Wesley, said, "We must immediately attack accounting problems under the philosophy of handling each business transaction as it occurs rather than under the present condition of batching techniques." These sort of themes in what he said in the 50s, the use of data for accounting, think about modern issues like blockchain. The use of data for transactions as they occur, think of real-time business. The idea of avoiding batching techniques, think of trying to use streaming instead of batch techniques like MapReduce. These are all present topics in modern computer science that have to do with efficient data management that were already being asked about in the 1950s. Right, so there's some age-old challenges, age-old back and forth between technology that get covered in this field. Now on the right, we have a picture of a Rolodex. And if you've seen one of these things, it is in some sense a database. All right, we've got data in the form of business cards, and we've organized that data. It's alphabetical by the last name of the person, if you're using your Rolodex, right? And it's even indexed, right? There are these little finger tabs for the first letter of the last names to let you find things quickly. It's a very organized collection of data. Rolodexes have been around forever, and they're a sort of early 20th century implementation of what you might call a database. Is this a database? Well, we said that Tinder was kind of a database. I think more fair to say that it's a database with some business logic, and that's a buzz phrase that's often used for the computer program that you have to write to manage the data in the database so that it fits in with its real-world usage. And then, of course, there's a user interface here that allows you to swipe and shows you pictures and so on. So all those together form Tinder. But, you can see that the business logic and the user interface for Tinder are pretty simple. And most of the value is, in fact, in the database. Here's a picture of the Kayak app. Is this a database? Well, interestingly, airline reservation systems were actually one of the earliest pervasive consumer uses of database systems. The first online airline reservation system was called Sabre. It was co-designed by IBM and American Airlines back in 1964. And before I started teaching this lecture, I wasn't aware of what Sabre stood for. I Googled it. It stands for Semi-Automated Business Research Environment. Very ambitious name for a R&D project in computing back in the 1960s. This is before there were things like databases, or database systems, I should say. So this was a custom system. It was kind of a database and application logic for the airline industry, which is an industry where it's very important to do transactions that are happening at multiple terminals at travel agents all around the world, right? They're happening simultaneously, and to try to make sure that those transactions are correct, that you don't overbook the flight, that you correctly bill the client, and so on. Sabre lived for 40 odd years as a live working service. So Travelocity.com was the web instantiation of Sabre. The Sabre company eventually evolved into Travelocity. Travelocity was only acquired by Expedia back in 2015, so actually kind of a standalone entity till fairly recently. Now, I don't believe Expedia still uses the Sabre software at IBM mainframes, but that software was used till, at least the 2000s, and the impact of that system has been quite profound. So the use of databases and applications does go way, way back, and we're still doing some of those applications today. So in the end, what is a database? I don't want to get into arguments about it. I would say a database is a large organized collection of data. Now, the word database is sometimes used when what we really mean is a database management system, which is a piece of software. We'll call that a DBMS for short. A DBMS is software that stores, manages, and facilitates access to data. All right, so there's the database, which is the collection of data. There's a DBMS, which is the software over it. And actually, those things can either be tightly or loosely coupled, depending on how you architect things. When we talk about database systems, we're often talking about relational database systems, which are the most commonly used and most mature kinds of database systems available. These are systems that include things like Oracle, or Oracle's open source MySQL, Teradata, SQL Server, PostgreSQL, SQLite, and so on. So the acronym for a relational database management system would be an RDBMS. And relational systems typically support SQL as a standard language for data description and manipulation. It's a language that was invented by IBM in the 1970s and was standardized on by the industry. Another thing that relational databases tend to support is what's called ACID transaction consistency, which is a way of talking about how the database guarantees that the data remains consistent in a way that application developers can reason about. Relational databases typically support durable writes that prevent data loss via recovery. And as I said, these are quite mature technologies. A lot of these systems have been around since the 1970s even, in the case of Oracle, possibly Teradata, and the 1980s in the case of many of the others. Now, the history of database management systems actually has deep roots here at UC Berkeley. What you see here is a map of relational database systems and their descendants, with time moving from left to right. So you'll see over in the 1970s, there were two initial systems, Berkeley's Ingress project and IBM's System R project, which is at the bottom. So the Berkeley genealogy is this area that's been highlighted in yellow here, and it starts with Berkeley Ingress, which was followed by Postgres, which then was adopted by many different companies and commercialized as open source. So deep roots here at Berkeley. Other Berkeley-based database systems that were founded from the initial Ingress group or other people at Berkeley include Sybase and Informix. So all of those sort of lineages trace back to right here at UC Berkeley. In the middle, you'll see Oracle, which was one of the first commercial systems that was released. In fact, it was the first SQL system that was released to the market as a commercial product, beating out IBM. And then in the blue, you see the IBM lineage. They had not one, but multiple relational databases that grew out of their research there. And of course, there have been other systems as well, as you can see on this chart. If you look in the slides, you'll be able to find information about where to go find this chart. It's pretty interesting. If you look at db-engines.com, you can find a ranking of the popularity of different database engines based on things like the number of mentions in Stack Overflow, Google Trends, job postings, and so on. And you'll see that just recently, January 2019, Oracle was rated number 1, MySQL, which is open source but owned by Oracle, rated number 2. Microsoft SQL Server number 3, Postgres number 4. That's the first fully open source system on the list. And then number 5, as well as number 7 and 8, are not relational databases. They're other kinds of databases. Okay, so database systems are not exclusively relational databases, and there are popular systems that are non-relational systems. But the top, the top energy is all around relational databases. Now, in terms of market size, so just thinking about this in terms of dollars and cents, here's the global database market. In 2017, so this chart's a little bit out of date, in 2017, this was over a $50 billion software market, so quite a big market. And you'll see that the green piece of these bars, the large fraction of these bars, is the relational database market. The relational market itself is over $41 billion, so in and of itself a very large market. And what's going on around the margins at the top are things like Hadoop and Spark systems and NoSQL systems. Okay, and we'll learn a little bit about both of those towards the end of the semester. These are more recent developments in software, but they don't really introduce any technologies that we won't learn during the course of our discussions earlier in the semester. It's sort of a different packaging and deployment of some of those core technologies that's appropriate for certain modern use cases. So we'll talk a little bit about market trends, what's going on in the database industry today. The cloud is disrupting the traditional database market in very interesting ways as companies increasingly move their database systems from on-premises deployments at their own sites into public clouds like Amazon Web Services, Microsoft Azure, and Google Cloud Platform. Now, interestingly, the cloud is somewhat less relational-centric than the traditional on-premises. If you look at the mix of deployments and usage of, say, NoSQL storage versus relational storage, there's more NoSQL storage proportionally in the cloud than on-premises. Still in all, the fastest growing services at the leading public cloud, AWS, are relational database management systems. Not just the fastest growing database services, the fastest growing services. So database systems are the fastest growing usage of anything in the cloud right now, and relational databases are the ones that are leading. Okay, one of the things that's happened in the market over the last decade that's been pretty interesting is the idea that one size of database management system doesn't fit all use cases. And you may want to use a special piece of software, a special database management system for special purpose use cases. One niche market for special purpose databases is what's called main memory DBMSs. These are relational database systems, typically, that are managing data that's big enough that you want it in a database system, and it's important enough that you want it in a database system, but it's not so big that it won't fit in the RAM of a large node. Okay, there's lots of database systems these days that'll fit into many, many gigabytes or maybe a couple terabytes of data, things that you can actually deploy in RAM. So there's database systems that have been tuned for that use case. There are also database systems that are tuned for particular kinds of data that have different access patterns or different query models than traditional relational queries tend to. So graph DBMSs are designed to handle graph data, the kinds of data you can think about in social networks. Time series DBMSs are designed to handle time series data like from stock tickers or from sensors. And then we talked a bit already about key value stores, the NoSQL movement, and analytics platforms for batch analytics like Spark and Hadoop being new kinds of data management systems that are a little bit different than traditional relational systems. So we'll learn about some of these during the course of the semester. But the thing to keep in mind is that there is likely to be more usage of these special purpose databases over time as it becomes easier to manage software in the cloud and deploy it. There's also a huge market, actually, of tools for working with data on top of database management systems. And this goes back to the 1990s with ideas like business intelligence systems, which are software for building charts and doing exploratory visual data analysis on very large databases. Okay, and so this is products like Tableau and Microsoft Power BI. There are new products emerging from machine learning and data science, new platforms for that are pretty interesting to watch. And then another traditional software category that's being renovated is this idea of data preparation or data wrangling. The work that you have to do to get your data cleaned up in order to analyze it, and then integrating data across multiple sources, which is also part of that preparation or wrangling of data. Traditionally, this market used to be called ETL, extract, transform, and load. And today, increasingly, we're seeing new energy around this data preparation space. Why are we seeing changes in the market? Well, a bunch of things. Hardware trends are changing. So RAM sizes are getting much bigger, which motivates things like main memory databases. The rise of solid-state disks over magnetic disks is changing the way that database systems are built, and that's going to affect some of our discussion in this class. We'll talk about that quite a bit. Even faster than solid-state disks, but still persistent storage, is the idea of non-volatile RAM, some of which is now being bundled with SSDs in interesting packaging. And then, of course, there's new trends on the computation side as well, like the use of GPUs, graphics processing units, to do other kinds of computing other than graphics. So there have been efforts to use GPUs for database queries. And all of these kind of changes in hardware trends will be reasons that we might change the architectures of database systems. As we've talked about, there are changes to platforms, so not just the individual components of the hardware, but the way they're deployed. So the cloud has been obviously the biggest change here. And the idea that compute in the cloud is elastic. You can have as much compute and as much storage as you want, but you'd only like to pay for as much as you're currently using. And then if you use more, you'd like to get it to be bigger, and if you start using less, you'd like it to shrink down. So that elasticity of resources does change the way we think about building database systems. Obviously, we need to scale our database systems more and more as both storage grows, so the need for storing more data grows, and as the workload, the number of transactions that we run on these databases grows through increasing usage. So those are two dimensions of scaling that we need to be able to do, and they may cause us to change our designs. As we've discussed, there's new data types emerging that are increasingly being used in database scenarios. So this includes things like full text, semi-structured data like JSON, image and video data that increasingly people want to query in database-like style. And then, of course, we've got new workloads over the data that are emerging in places like machine learning, advanced analytics, and AI. So all in all, there's a lot of change going on in the database space that's going to cause the ideas that you learn in this class to be remixed and reinvented and applied to new settings. And so it's really important, as we said in this class, to learn the principles and be ready for change. This change is an opportunity. As I said, the world of database management systems is changing. Our textbook, just by the way, is rather out of date. It's from 2003. Both of the authors of the textbook are now no longer professors. They're senior executives at Microsoft. So they've taken their academic work and they're out there applying it to the next generation of technologies on the desktop and in the cloud. And there's a real opportunity for you as well, based on what you're learning in this class, to shape the future of the database management systems, both the ones we invent in our research and the ones that we deploy out in the industry. So we won't be following the textbook slavishly. What we're going to be doing is taking advantage of the core ideas in the textbook to give you the tools to exploit the opportunity to build new systems as the database market changes. So we're going to focus on those foundational system principles, the reusable ideas and components that we're going to learn about in this class. And we'll have a compositional approach. We'll show you how to build those components into a stack, how to put them together with APIs between them in order to build different kinds of systems. And our goal, of course, is for you to be able to use existing database management systems. So we do want to give you some core skills just to use the tools that are out there today, but also to build new ones. So in this class, you'll learn how to do data-oriented programming with SQL, specifically how to program in a declarative way, where you say what you want to get out of the database, but not how to get it. And that's a very different style of programming than you may be used to. We'll learn foundations of data system design, issues like storage and indexing of data, techniques like query processing and query optimization for translating queries into executable strategies that we can run on our computers. We'll learn about the notion of transactions and what it means to have correct interleavings of multiple users' queries and updates on the same data. So we'll look at issues like concurrency, consistency of data, and recovery of data during crashes. And then we'll also talk about data modeling, the idea of how do we represent information that we care about, say information in the real world, as data in a database, and how do we make sure that that representation is faithful? So what are application level representations of the data we want in the real world? These are all techniques and ideas that we'll learn in this class. And underneath those techniques, there are some principles, which you might not learn about in any other class but a database class. The idea of data independence, which we'll talk about very soon in some of the early lectures in this class. The idea, as I said, with SQL, of doing programming in a declarative way, where you say what you want, not how to get it. The notion of rendezvous of data in time and space, and also rendezvous of requests and responses in time and space, and how that relates to the notion of relational joins, both on a single node and across multiple nodes. But not only to joins, but really to the core of many things we do in computing. We'll learn about isolation of different actors that are running at the same time in a system and the consistency of their actions on data. And then, as I said, we'll learn some principles about data representation. So all of these are foundational principles that underlie some of the topics we talk about in this class. We will learn about specific systems and how to put them together. So we'll examine the various levels of a DBMS. This is going to be our reference block diagram for a relational database in this class. And we'll use the various boxes in this diagram as reference points for what we talk about and learn in the class. We'll also see how these boxes and layers fit together to form a complete and rather complex system out of some self-contained and modular parts. So in sum, the class is about the big ideas in database management system principles and algorithms, architectures and system designs. And as I said, this is really the heart of scalable computer science. How do we build systems that really can run on lots and lots of data?